Hello, I'm Anh Tuấn Hoàng, and welcome to our first lab, Lab 0 on Architecture and Networks. This is outline of our lab today. We will do experiments on arithmetic operations and register operands, arithmetic operations and memory operands, arithmetic operations and immediate operands. We will do the representing instructions in computer, and finally we will make the first LACVS program code. I will use two documents in our lab, the lecture number 2 and 3 that you already attend. Information from that lecture, from those lectures, should be appeared in our lab like this. A second reference that will be used is LACVS reference data, and it should be appeared in our lab like this. Detail of our lab requirement. The experiment from number 1 to number 8 can be found in this document. As you can see here. And the second reference data that I mentioned before, the LACVS reference data, can be found in this document. You can find all the instructions in LACVS here. You can also find the instruction format here. The register available that can be used for many kind of purpose can be found here, and also the opcode for those instructions can be found here. One more tool that I will use in our lab, that is the calculator in programming mode. Here you can see we can use the binary mode. We can write something in binary, and that binary number can be converted into decimal number or hexadecimal number. Of course, you can also change the format of the number here to convert it from other kind of format. For example, here from decimal format into hexadecimal or into binary format here. Well, now we will go into our first experiment, the arithmetic operations and register operands. The question is, we will consider this C code F equal G plus H minus I plus J, and we will need to find the equivalent LACVS code. As we can see, this equation includes several computations, and so we will need about 3 steps to find the LACVS code. At the first step, we will decide the computation sequence. The second step, we will decide the location or the register for each operand. And in the last step, step 3, we will apply the LACVS assembly code to the equation. Here in step 1, I decide that we will do the G plus H at first, and then we do I plus J second. Finally, immediate value of G plus H will be used to minus value of I plus J here, and we will have the final result located in F. In the second step, we will need to decide where are these values, which register should be used for those values, which register should be used for immediate value and the final value. In order to do so, we look into our LACVS reference data. We can see that we have 32 registers numbered from 0 to 31. Among those, we have many special purpose registers like register from 0 to 7, register 8, register 16 to 18, register 28 to 31. So this register should not be used as immediate value or as immediate or as variable in our program, and so we should use register from 9 to 15 and register from 19 to 27 in our equation. With that, I decide that we will store value of G in register 20, value of H in register 21, and I in 22, J in 23. The immediate region of G plus H and I plus J will be stored in register 9 and 10 respectively. Finally, the value of G plus H minus I plus J will be stored in register 19 or F in this case. After we make this decision, we will go to step 3. We will need some addition for G plus H and I plus J here. After that, we will need subtraction. So I will look into the addition first. We will come back with the LagVH reference data. We can see here we have several add operations in which this is add with immediate, and set flux, add and set flux. And so we can see here we need to calculate the addition, the sum of G and H only. So we will use the add. This should be the appropriate operations in this situation. And the format of the add instruction is RD and then RN and finally RM, in which RD, the destination register, will equal with the value in RN plus the value in RM. So we know that we should write the instruction like add, RD, RN and RM. We look into this. We have RD, the destination is X9, RN, the first operand is X20, and RM, the second operand is X21. So our instruction it looks like this: add X9, X20 and then X21, in which X9, the immediate value here, will equal to X20 or value of G plus with X21 or value of H. Similarly, the second addition I plus J will be calculated by add X10, X22 and then X23, in which X10, that is in immediate value, the region, will be equal with X22 or value of I plus with X23 or value of J. The next one is the subtraction. The subtraction here. So we will need to look again into the reference data to find the subtract. We have several subtract. The subtract with immediate, and then set flux. The subtract and set flux, and appropriate instruction should be the subtract. So we will use the instruction like sub, RD, RN and then RM, in which RD, the destination, will equal RN, the first operand, minus RM, the second operand. So we come back to our equation. We know that the destination RD will be X19 or F. So here RD is X19. The first operand G plus H we have here X9. so x9 located here, and finally the value of I plus j is x10, and so x10 will be located here. So we will have x19 or f equal x9 or g plus h minus x10 or I plus j. So we will have the code for this equation. It will include 3 lines of code, 2 add and 1 subtraction. In combination, we will combine everything together, and for easy understand, this equation will be turned into these 3 instructions: add x9, x20, x21, in which x9, that is temporary number 9, equals g plus h. The second instruction, add x10, x22, x23, will be temporary 10, equal I plus j, these 2. And finally, sub x19, x9, x10, which is f, this one, equal temporary 9 or g plus h minus temporary 10 or I plus j, calculated here. Well, now we will go to the second exercise, the arithmetic operations and memory operands, in which we will consider this C code. The 8th value or the 8th element of A memory will be added together with a variant H and then stored in variant G. So what is the equivalent lag V8 code for this C code? Similar with the exercise 1, we will consider this in 3 steps. Step 1, we decide the computation sequence. Step 2, we decide the location for each operand. In more detail, we will need to decide the location of data A in the memory, or it is the base address of data A in the memory. We will need to know the offset of the 8th element from this base of data A, and we will need to decide the location for G and H, which registers are used for G and H in our processor. And in step 3, we apply the lag V8 assembly code to the equation to find the final code. Now we will look at step 1. We will look into our 8 instructions. We can see that we have no 8 with memory, and so we can't directly apply G equal H plus A8 in this. So how can we solve this problem? We will look in another document, another place of our reference. We can see that among the instructions, we have the load instruction. The load instruction will load a value from memory into a register. So we can consider a solution for this calculation, like we load the value, the 8th value of A memory into a register, and then we add that 2 registers together and store it into G. So we know that the first step will be loading the value of the 8th element value of memory A into a register, and then we need to add that value, that immediate value, together with H to have G. And here is a reference back from your lecture. We know that the inside the memory, the data will be stored by 64 bits each. because you use double word. So the first data, the offset of the first data will be stored number 0. The second data will be stored in number 8 because the first data has 8 bytes. And similarly, the third data will be stored in number 16. And so we know that the offset for the 8 elements in our memory will be 8 by 8 equal to 64. So the offset address of this data will be 64. So next we will go to step 2. And so we look into our register. In this table, you can see that the same with the exercise number 1. You can see that we can use X19 to X15 as temporary memory, temporary register, and also X19 to X27 can be used as a temporary register. So we decide that the base address for data A will be stored in X22. The value that we load from memory from element number 8 of memory A will be stored in register X9, and value for H will be stored in register X21. And so the value for G will be stored in register X20. So we will have value in 20 equal with value in 21 in register 21 plus with the register value in register X9. Now we will go to step 3. The LACVS code, as we can see from this table before, we will use the load register unscale offset LDUR, and the format of this instruction is LDUR RT and then memory location or the base location of the memory A RN, and the next is data address, that is the offset address of this number 8. So the load instruction will be appear like this: LGUR and then X9, the destination location that we store value of the memory, the element 8 of the memory X9. So X9 located here. The base address of the memory A, which is stored in X22, will be located here. And finally, the offset address, which is 64 as we calculated here, will be located here. And the next one, we have the addition. It is completely the same with exercise 1. So we have 8 X20 or register for G, X21, which is the register that store value for H, and then X9, the register that store the value come from memory. So this instruction will add register 21 together with register 9 and then stored in register 20. Yeah, if we combine all those things together, we will have 2 instructions here to show this equation. LDUR X9, X22, and offset address value of 64. It means temporary register 9 will be the value loaded from memory A at the 8th element, at the 8th location, and then we add X20 x21 and x9, which means G or register x20 equal H or register 21 plus temporary register number 9. Well, now we will move to the exercise 3, another exercise on arithmetic operations and memory operands, in which we will consider the following C code. If we look into this and make comparison between this and the one in exercise 2, we can see that instead of G, which can be considered as a register in this equation, we will replace it by A12, the 12 element in data A stored in a memory. So we will follow the same 3 steps with the exercise 2 to show this problem. But in step 2, we will need to decide the location for data A, or another word, in which register the base address of the data A will be stored, the offset address of the 8 and the 12 elements from that base address of data A, and of course the temporary and the H register, and the register used for temporary and H. So in step 1, we know that we will have the load register for loading this value into a temporary register. After adding them together, we will need to store it back to the memory. So we will have 3 steps or three operations. At first we will need to load the 8 elements of the A data from memory into a temporary register, and then at the second step we need to add this value together with H, which is stored in another register, and then at the third operations we will need to store this value back to the memory, and we will need to decide what is the offset address of the 8 and the 12 element in memory. We know that each data in the memory will be a double word, which is 8 bytes. So the 8 elements will be stored at the address of 64, the offset address of 64, and the 12 element will be stored in the offset at the offset address of 96. And the same with we will do the same with another exercise, and we can see that we can use temporary register x9 to x15 and x19 to x27 as the register to store the data from the memory or from the temporary, as well as the value of H. So we decide that the base address of A in memory will be stored in x22, value of H will be stored in register 21, and the 8 elements, the value of the 8 element in the A memory will be loaded into register 9. So in the third step, we will do the calculation. At first, we will need to load from memory. We already have this instruction before, that is LGUR x9, x22, and the immediate the offset address of 64, in which the 8 elements of the 8 elements of the memory A, which is started from the address shown by x22, will be loaded into register X9, and then the addition will occur, in which we use the instruction add X9, X21 and X9, which means that the value inside X9 will be replaced by the value of X21 plus the old value of X9. And finally, we will need to store the value inside X9 into the 12 elements of memory A. And so we use the STUR, X9, X22 and the offset address 96, which shows the offset address of the 12th element, and X2 will be the base address of A in the memory, and X9, which is the region of this H, or another word, X9 is the value of H plus with the value of the H element in A. So in combination, we combine all together, we will have these three instructions for we will need to use these three instructions to show the problem of this C code equation. Next, we will go to exercise 4, which related to working with immediate operands. Here you can see the C code I equal I plus 4, in which 4 is an immediate operand, and I we can consider it as a register in the CPU. And so we will need to follow the same three steps for deciding the computation sequence, deciding the location of the register for the operand, here the operand I, and applying the LACVH assembly code to the equation. So I hope that you still remember that in the instruction list we have an instruction that add a register together with an immediate value, and so we will need only one instruction or one operations to show this equation. In step 2, the same with other exercise, we will use register from X9 to X15 or X19 to X27 as the register for value of I. And in this exercise, I decided that I would like to use the register X22 as the register to store value of I, and we will have the immediate value 4 here, which will be extracted from the instruction. So in step 3, we will need to look again to the LACVH reference data to find the addition with immediate, and we can find it here, HI, in which I in format I, and it has the instruction has format of HI, RD, RN, and immediate value, in which RD is the destination, and here it should be X22. RN is the operand, and it is X22 2, and the immediate value, which is 4. And so we will have the addition instruction HI, X22, X22, and immediate value 4, which means that the value of X22 will be replaced by its own value plus with the immediate value 4. So here is the combination code. We just need only one code, one instruction to show this C code, and so this is the instruction we need. Next, we go to exercise number 5, representing instructions in the computer. We will consider this lag-prefied code 8, x9, x20, x21, which means that value inside x9 register will be replaced by the sum of value in register 20 and value in register 21. These two added together and written into x9. The question is, what is the equivalent machine code in decimal, hexadecimal, and binary? In order to solve this problem, we need to follow these 3 steps. In step 1, we need to find the format of the instructions. We need to know what is the instruction type, the operands. And in step 2, we need to find the format and instruction in machine code. And in step 3, we need to convert the machine code into the number either in decimal, hexadecimal, or binary. So in step 1, we look into LAGVH reference data to find the 8 instruction, and we can find it here. The 8 instruction, it has the R format, so we know that it is R format. We look into our lecture, we can find that R format has the form of 8 RD, say for destination, RN and RM says for 2 operands, in which RD will be equal RN plus RM. And so we look into this instruction and the format, we can know that RD here will be x9, RN here will be x20, and RM here will be x21. So I write those values here for the later use. So in step 2, we will look into the instruction format of the R instruction. We can see that the opcode has 11 bits from bits 21 to 31, and then RM located here. This value we will not use at this time, so we don't care about it. And then RN located here, and RD. In your lecture, you can see that you can see it like this. We have opcode which takes 11 bits. RM takes 5 bits. This is not important at this time, but it takes 6 bits. RN needs 5 bits, and RD needs another 5 bits, and their location will be like this. For step 3, we need to know what is the opcode for the 8 instruction, and so we look into the opcode. We can see that the 8 instruction here, it has 11 bit opcodes, and the value is 1000, 10110000, and so we will have this value, this 11 bit value located here as opcode. RM, we know that RM here is x21, so 21 located here. For this part, we just fill it by 0. For RN, we know it is 20, and so 20 will be located here in decimal format. And RD, here the value of RD is 9, and so here we have 9. So the mixed code, the mixed machine code will be this binary value and this decimal value connect together. And now we need to convert them into another format. If we need the decimal format, this value we will take the we will need to know what is this value. So as I told you before, we will need to use the calculator to find that value, which is this value in binary this value in binary, it is equal to you can see that this value in binary equal to 2130. Oh no, 1112 in decimal. So we come back to our slide and we convert this into decimal. It is 1112 in decimal, and another value like 21, 20 and 9 are still in decimal, so we keep it like this. This all 0 bit will return to 0 in decimal also. Now we convert all these value into binary, so these are binary already, so we just copy it here. The value 21 in binary, we will need to check it. So 21 in binary, 21 in decimal, we will write it here 21, and we can see that for the 5, if it takes 5 bits, 1 2 3 4 5 bits, and the value will be 10101. And so the value here 21 is 10101, and similarly we have value 20, that is 10100, and 9 it is 01001. Of course, if we combine all these binary value together, we will have its value in hexadecimal. Now we can do it by this. Now we have binary. The binary is the connection of all these value together, and here you can see the hexadecimal value of it. It is 8B18 8B150289 in hexadecimal. And so that hexadecimal is written here. And next we go to exercise number 6. We will check how the LagVH code is represented in the computer, but instead of working with 8 instruction, now we will work with LGUR instruction, and we know that LGUR is the memory, the working with memory instruction. And so the question is, what is the equivalent machine code in decimal, hexadecimal and binary? And of course we know that this instruction will be in another format, and we will follow the same 3 steps to know what is the machine code for this one. So at the first step, we need to look into the instruction table, and then we try to find LGUR instruction. It is here, LGUR, and we know it is a D format. For the D format, the format looks like this: LGUR, the instruction, and then RT, say for the target, and then RN and the offset address. RN is the register that keep the base address in memory, and we make comparison between this format and this instruction. We know that RT is X9, so RT is X9. RN is X22, so 22 is here, and the offset address, it is 64, and so 64 is here. So now we know that RT here, RN here, and address here. For step 2, we will need to know the code instruction format for the D type, and we can see D type here. We have opcode, and then the offset address, this address, and then this part operation, but we will not use it at this time, and then RN, and finally RT. If you look into your lecture, you can see that this opcode, again, it is 11 bits. This address here, it has 9 bits. The operands are 2 bits, but we don't use it at this time. RN and RT, each of them will have 5 bits. And now we need to know what is opcode, what is the machine code for, or opcode for LDUR. And we look into this table, we can find LDUR has 11 bits for opcode, and the opcode is 1111100010. And so the opcode written here, we just copy it from here to here. The address, we know that it is 64, so 64 here. This 0, RN X22, so value 22 located here, and RT, it is X9, so we put 9 here, and we have the mixed code between binary and decimal. We need to convert all this into decimal, so we use the calculator to convert this binary value into decimal, and we have this 1986 in decimal, 64 are the same, 0 will be 0 in decimal, and 22, 9 are the same. If we need the binary value, we just convert this 64, 22, and 9 from decimal to binary. For binary, we will need 9 bits for address, 5 bits for RN, and 5 bits for RT. And so 64 in binary will be this value with 9 bits, and 22 will be this, and 9 the same, it is 01001. We connect all these binary together, and we will have hexadecimal value for this instruction. The exercise 7, we will need to know what is the machine code in decimal, hexadecimal, and binary for this lag VH code HI, X9, X9, and 1, which means that X9 equal X9 plus 1. We already know that this is 8 with immediate value, and so we know it is I format. The I format has the format of 8, RD, RN, and immediate, and we look into this, we can see that RD is 9, RN is 9, and immediate here is 1. And the opcode and the format for the machine code format for this instruction will be opcode for 10 bits, immediate value use 12 bits, and then Rn and Rd each has 5 bits. So we look into the opcode tables and find the Si. We will have the value, this value, and immediate, of course, it is 1 here. Rn and Rd, both of them are x9, so we have 9 and 9 here, and we have the code in mix between binary and hex and decimal. Convert this into this decimal, we will have the value of 580 in decimal, and all other are keeping the same 199. Converting them into binary, we will have 1 will be 11 bits of 0 and the final bits of 1. Value 9 will be 0, 1, 0, 0, 1 using 5 bits, and so these 5 bits are written here. We connect all these bits together, all these bits connected together, and we will have the hexadecimal for this instruction showing here. Next, we will go to the last exercise. Our first LACV8 program code. We consider about this C code, and we need to change it into the equivalent LACV8 code. In order to do so, we will try to reuse the previous exercise as much as possible, and in more detail, we will think about exercise number 1, 3, and 4. If you look into this code, you can see code that are written in blue can be taken from exercise number 3. Here you can see that we have a register. The value inside a register is loaded from a memory similar with this, and a register added together with a value in memory, which is this one, and we also have the store a value from register to a memory like this. The code in yellow here will be the operation working with immediate value, so it is exercise number 4. The red code is exactly the exercise number 1. And in order to solve this problem, we need to decide the register for each variable h, g, I, and so on. We also need to decide the base address for the data A in memory. We also need to calculate the offset address for each data element in the memory, and so we decide the F will be represented in x19, G in x20, H or the value loaded from A1 will be in x21, I the value loaded from A3 will be in x22, J the value that the region of I plus 1 will be temporarily stored in x23, G plus H here will be stored in x9, the same with what we do in exercise number 1, and I plus J here will be stored in x10. The value that will be loaded from A2 will be stored in x11. The base address for data A will be stored in register x24. We will know that in memory, one data element is a double word. It takes 8 bytes, and so offset for the data A1 will be 8, A2 will be 16, and so A3 will be 24, and A12 is 96. Now we will change from C code to LACV8 code using our decided register and base address. For the first code h equal A1, we know that we need to load the value A1 from memory to register h. We know that h is x21, base address for A is in x24, and the offset address for A1 is 8. So we have load LD UR x21, x24 and address 8 here. The second C code will equal with 2 other lag VH code. The A2 which has the offset address of 16 will be stored into x11, will be loaded into x11, and then that x11 will be added with x21, which is 8, and stored in x20, which is G. The next instruction will be another load instruction from A3 to I, and so I is x22. A3 has offset address of 24, and so we have load UR x22, x24, and from the offset address of 24 here. The next code we work with immediate value, and so we use completely the same instruction with what we have in exercise 4. HI x23, that is J, x22, that is I here, and the immediate value 1. The next code that is completely the same with our exercise number 1, and so we just use the same code with exercise number 1 here. And finally, we will need to store the value f calculated here into the memory A12, and so we know that A12 has the offset address of 96. The base address of A is in x24, and f, that is in x19, so it will be store UR x19 from x24 and offset address 96. And so that's all for our lab today.